Alright, today we're going to be doing problem number 2 from homework number 2. It actually has two parts, an A and a B, and we're going to begin up here. Part A basically just asks us to describe this by actually drawing out this equation right here, okay? Such that the alpha and c variables are positive constants, and we're using this unit step function as defined right here. And if we draw it out, it's basically drawn out like this, which we'll describe in a minute, but we can see how the function is basically starts to be defined at the c value, jumps up, then has this curve. Now, how did we get that? If we look at the component functions right over here, this function corresponding to this pick, and this function corresponding to this drawing, we can see that 1 minus e to the negative alpha times x corresponds to this graph right here, at which point it plateaus over time, plateaus as x increases. It plateaus toward 1. So that's our basic equation, and then it kind of dips down over here. Our unit step function, on the other hand, is basically, according to this, only defined when x is greater than 0. All right, which the only way that's going to be is when x is equal to c in this case. So once we hit the value of c, the unit step function is defined as 1, and before c is defined as 0. Now we can see if we actually take the product of these two terms, looking at the graph, these two graphs, we can see that values below c will cancel out. It's basically product times 0. Corresponds to this. And after that, we're basically multiplying this function times 1, which corresponds to this curve right here, which we show right here. And that's how we actually get the drawing for our cumulative function here. Now, is this probability distribution valid? Well, yes, it is. And we find out that this is so because it abides by all the properties of a distribution function. For instance, as it goes toward negative infinity, it equals 0. Toward infinity, plateaus to 1 as we described. It is non-decreasing. It's always increasing. It is non-negative. You can see that. And we can see how it's continuous toward the right. The one issue with this continuity right here, it's a little bit of concern, is that how this unit step function was defined in the homework, it actually excludes 0. It only showed a greater than or lesser than. I believe this term needs to be greater than or equal to in order to actually work out. I'm going to assume it was just a small error, and otherwise there is a point in discontinuity at c. But that being noted, I'd have to say that this equation is valid. Now, moving on to part B. Part B basically wants us to actually find and draw out the density function that corresponds to this big F of t. Now, the way we do that by definition is that basically we take the derivative of big F of t up here, and we play it out. And we see right here, we take that equation, we find a derivative, which is basically this term times the derivative of that term, plus that term times the derivative of this term. Now, as is defined, the derivative of the unit step function is defined as the delta function, the Dirac formula, which we put right here. This remains the same. And this just by basically finding the derivative using properties of E, we can actually play out. It corresponds to this equation here. We bring this down. We do a little bit of arithmetic right here. We just rearrange terms. This term right over here. All right. The one difference I'll note is that Dirac is only going to be defined at c. So we can actually make this a constant term by replacing the x with c, which we did right here. And we just use the Dirac formula. So that's our final formula for small f of t. And if we draw that out, we can see how it corresponds to this figure right here. Basically, using this portion of the equation right here, we can see how it corresponds to this line right at C, as you see right here, defined specifically at the meeting point by this constant. And then the rest of the curve is defined by this term, which is 1, times this equation right here, which corresponds to this decreasing curve, as we see here. It seems to plateau at the x-axis. Now, the question at hand is whether we can verify the validity of this density function. And the way we go about doing so is basically taking the small f of t and seeing if we can get back an area of 1 by taking the integral over negative infinity to positive infinity. So we do that right here. We substitute in our calculated f of t right there. As you can see right here, because of the unit step function, basically it's only defined after x is equal to c. So we can redefine this portion of the integral as c to infinity, which we do right here. As we described, this term is a constant, so we can take it out of the integral, which leaves us with this negative infinity to positive infinity of the Dirac formula, which by definition is equal to 1. So if we take down the terms, do a little arithmetic, we see these terms cancel out, and our overall integral is equal to 1. Thus, given that our small f of t is a non-negative, as we can see here, and the area under the curve equates to 1, we can conclude that this is a valid density function. Hence ends the proof.